All right. We're doing the point 6 of 12 here, which is the second of the lecture 12s that have to do with cyclic dynamics for n objects. But we're going to be talking about a continuum of states more today than anything else. And I want to also, with this particular continuum, talk about the distinction between a pulse wave and a continuous wave, and the ideas of uncertainty in both space-time and per space-time, which involves the wave vectors, wave numbers, numbers per space, numbers per time. Frequency is what we're talking about there. Now the beat dynamics and revivals due to the dispersion function that is the simplest one, the one that's used in all of Schrodinger mechanics, the quadratic dispersion, is the main topic today. And it's really quite spectacular and a lot of fun, and it's pretty complicated looking, but we're going to have ways down here. This is some number theory down here that sort of a physicist number theory that really has, I think, a lot of applications. But we'll be seeing a very complicated quantum fractal behavior. This is a generalization of the basic wave dynamics that we've seen already, the beat dynamics between two eigenstates. But we're going to have more than two. The more the merrier. And as you get more and more, you start to see the fractal behavior occurring in space and time. Now we're going to take and compare first the infinite square well. That's number one problem in most of the quantum mechanics that we teach nowadays. And perhaps this even simpler case, I call it the Bohr rotor. It's the Bohr atom, but only with angle. So you imagine that you've got a wave confined to a ring. Even simpler than the Bohr atom. These two problems are homomorphic. That means this problem here is contained within this one, and that's important to know for the next lecture, where we'll be putting rings together and then taking them, putting scissors to them and changing the boundary conditions. And that's really the only difference between these two, but it's a big difference in some ways, symmetry ways. So, after we've compared the infinite square well and the Bohr rotor, we're going to do the square well wave dynamics. We're going to study a certain kind of wave packet and its uncertainty. And then we're going to see this marvelous process where this wave packet explodes, literally going to look like a detonation. And then it's going to undetonate, unexplode. This is really cool. So this part is lots of fun, and we're going to redo it for the Bohr rotor. That's where you can understand it. Turns out this is the one that has the simplest symmetry description, so we'll be using it. And we'll also try different wave packets. The Gaussian wave packet, we need to learn what its properties are anyway. So here's a good chance to see it doing an explosion. This is an explosion with a bang. This is more like a poof. And it unpoofs, as you'll see. In the process of making a space-time fractal, space-time coordinate system with mileposts is what I call it, because as you'll see, you can actually mark off space and time with a phase. But in the process of building that, we need to understand a fractal by looking at the elementary arithmetic of fractions. And if you ever have to teach children fractions, and if you remember your own teaching of fractions, you probably had some doubts about them. That is, they seemed uncomfortable. A lot of people have trouble learning at the young age. This is a beautiful way to teach it. And it involves something called the Fourier sum, which goes back to 1815, study of tide resonances, and the Ford circles, Ford geometry, Ford arithmetic. That's 1931, and really not too well known structure of mathematics, which we're going to make use of. So the phase dynamics of cyclic groups will emerge after that, if we have time. I'll also show you the monster mash, which is also related to all of this. So let's get started and see the two archetypes. Just giving you a rough description here. One of them is a pulse or a train of pulses, and the other one's just a train of cosines, sine waves, plane waves moving. So this is space and time, space, here, time. We use a similar graph to make the relativity entree. This is a more simpler use of that picture. So these are the archetypes of light waves. You really need to be dispersion-free for these pulses to behave so well. The ones we're going to study in the Bohr thing explode. So this is not a diagram for anything but a light wave. It needs that speed of light to be the same for all colors. So there's one Fourier component. Now, the PW, or particle-like wave, or pulse wave train, is this. The second, the CW, stands for a coherent state wave, or continuous wave. That's the proper jargon, CW. Everybody knows what CW if you're an experimentalist in laser optics. CW also stands for cosine wave or colored wave, a wave of definite color, whereas this one is a mixture. Now here you should see the comparison. The PW amplitude is 0, practically 0, everywhere except here, here, and here. So it's a wave that knows where it is. That's defined by where it is. Has sharp peaks. Zeros, not. This one's just the opposite. Mostly non-zero, except here, here, and here. This is the real part, of course. So it has sharp zeros, and is best defined where it is not. So those are the two archetypical opposites, you might say, in terms of Fourier space-time or per space-time. We're going to make the most simple wave packet or pulse by simply adding cosines of equal amplitude and higher frequency. Cosine phi, cosine 2 phi, cosine 3 phi, cosine 4 phi, and so forth. Add them all up. And that's what you get if you stop right about 10. Okay? So as I said, this one has mostly 0 in here, and certainly if I squared this, you wouldn't be able to see much in there. But it has a whole bunch of zeros. We have to talk about that later. But in one place here, right here, and then again at 2 pi later, they all add up to constructively interfere to give a maximum that's roughly 10 times higher than the next thing here. So these CWs, these color waves, or Fourier spectral components, are being shown very graphically here. Now, you can go backwards on this. It's vice versa. CW forms could be made artificially with a bunch of pulse waves. This is kind of what they do in digital sampling and digital analog synthesis, pulse packets, okay? But as we'll see, this is a terrible way to make a quantum CW. It would not work. This works, that, very questionable. Okay, now I'm going to compare uncertainty in space and time with uncertainty in inverse space and time. So here's just one cosine wave. And in per space-time, we'd indicate that as a single line in a scale of 1 through 50, and only one is available. Well, you could say there's a little, you got to have a zero frequency, so I could put this thing anywhere using the zero frequency. So there's really two lines there, but that's a little bit of a quibble. In any case, what's interesting is that this is a single period and has a tau, a time, that's very definitely indicating where this thing has its trough. But if I were to add a half amount, so these were zeros, that would be a good definition of its uncertainty in time. And this one, well, the uncertainty is 1 over time, if you want to count that middle guy. Okay, next one, 2. Okay, it brings these this point in by a factor of 2, and then 3, 4, 5 brings it in by a factor of 5. So as I add more, my uncertainty goes up to 2 here, up to 5 here, 6, 7, 8, 9, 10 here, 11, 12, 13, 14, 20, 30, 40, 50 here. By 50, wow, you see, little tiny width there, which we're going to calculate later on, tau over 50. Okay, so we've divided this period up into 50 pieces, and only that region right there is appreciably non-zero. Whereas out in bandwidth, wow, we've got a lot of components there, 50 of them to be exact. So this is the basic idea of uncertainty. Fourier uncertainty, but put h bar on this and you got Fourier Heisenberg uncertainty. The h obviously would go, if I was going to call that energy, I put an h bar on that and I have a delta E, then I get an h bar there. So that would be the time frequency uncertainty relation. And this dimension is time, this dimension is frequency or per time, you see. It's just a simple fact that this is the inverse of that. That makes uncertainty really not so mysterious. And you could do it in space too. If it's space, then this dimension is wave number or per space. That would be a delta x, delta kappa equal 1. Okay? So that takes a lot of the mystery out, but there's still a lot of things that to do with this, and the idea is that this is more wave-like, to have few or just one Fourier component. This is more particle-like, to have a whole bunch of them in a particular arrangement that we're using right here of a simple sum. This one is very prone to the interference effects that gave us the relativity in a very nice way. This one is not so. This is not prone to interference, except in the regions where it's non-zero, and then you have to look very carefully, and it's very complex, depending on the pulse wave that you make. So, that's that, and then I would like to make a comparison now of the theaters that we're going to run these waves in. Bohr rotor turns out to be the one that we'll use the most. And unfortunately, it's the one that is not explored in very much detail, even though it's the simpler of the two in many respects. For our symmetry purposes, though, we will be referring to this quite often as we develop the techniques of symmetry projection for Fourier states. But this is to be compared with the infinite square well, where I've simply filled up this entire region of space right here with concrete. Well, I've put in a huge something, electric field or something, if this was an electron being trapped, a huge the wave that's remained, and squeeze the wave out of this region. And, well, what's cool is if I make this distance the same as this distance right here, that is this and this are the same distance, I have the same eigenstate wave. There I have, starting with sine of 1 times the angle or coordinate phi, and we are thinking of angles, as I'll point out in a minute here. Sine of 2 times phi, sine of 3 times phi. You see, here are 3 whole waves on a ring. We might as well show the ring that we're going to put it on. We're going to take this graph, or this graph, and literally wrap around a ring so we can plot energy versus angle as we talk about the waves here, starting with 1, 2, 3, and so forth. And the thing to notice, a couple of things to notice qualitatively, is that this problem here, every one of these levels is doubly degenerate except for the first one. The first one I haven't bothered to draw, but it's just basically a constant wave. It is a wave that has no wiggles at all. The Fourier component 0. That one, m equals 0. Our magnetic quantum number, our momentum number that we talked about, when it's 0, everything's the same phase. Imagine an infinite number of phasors here. They're all synchronized clocks. Not allowed over here. This is forbidden over here to have that. Now we're going to, as I say, wrap this thing around. We can do it with both of these, but I'm particularly interested in this one, so that I make these two ends meet. You see, they're meeting right here in this picture. I turned this one a little bit this way, okay? So this is basically this diagram right here pasted onto a cylinder, okay?
I didn't get the idea of M0.
Okay, M, as you remember, was a count of the number of waves.
Yeah.
Okay, that's perhaps the most elementary definition of a quantum. You're
Number
quantizing
of wavelengths.
Yeah, wavelengths if you're doing geometry, right? So this one has one whole wave wrapped around and meeting itself coming the other way. Okay? This one has no waves. It just does this, if it has a frequency at all. And this particular Hamiltonian, we're not going to let it have even that. We're going to call that the origin of energy. So it just sits there, it doesn't do anything. But it's the S state for an atom. An atom has no wrinkles in the S state. You see, and that's true of the Bohr atom too, but certainly true of the Bohr ring. Okay? Does that make sense? Okay? And then you get to have only integer quantized, quantum, integer quanta of wave. You can't have half a wave here.
But
not here.
We just, for harmonic oscillator, we have just...
Well, the harmonic oscillator, you see, is a
M0,
nice
for,
curve potential, right?
But for Bohr atom, we don't have M0.
Yeah. No,
It
harmonic
starts from
oscillator
one.
has a 0-point energy, like this thing. And there is no, you are not allowed to have a state at this energy. This is the first one. Whereas this is the second level here. You've got this one counting as the first. But this is like the count from 0. So we have 0, 1, 2. When we have 0 but with nothing there, 1, 2. Over in the infinite square well analog. Does that make sense? Okay.
What is wavelengths? Wavelengths can be very small for the M0, or it doesn't exist.
Are you talking about the splitting or?
No,
It's
the M0.
infinite,
Oh,
undefined.
oh,
Undefined.
oh.
it approaches wavelengths of
Infinite.
M0.
Well, here's the best way to say it, is that I am allowed on this side to have two kinds of waves that are orthogonal to each other. Two kinds of real waves that are orthogonal to each other. I can have the cosine of 1 times phi and the sine of 1 times phi. Those are orthogonal. Okay? So I have a doublet, a double degeneracy on every one of these levels up to as high as you can go. And always you have a cosine and a sine. Okay? So, I'm allowed to have cosine of 0 phi, because cosine of 0 is 1. Sine of 0, sorry, we're not going to allow that. This is the first one. And there's no cosine to go with it. All of these levels are singlets. That is a single state, not degenerate. They are non-degenerate. This is the first example of a degeneracy that you would see in, going through this quantum mechanics. Not there, but here, here, and here, and so on. Always two states, sine and cosine. Or moving waves can happen here. I can have a green C-type motion here. I can have either e to the plus I phi, right circular or left circular polarization of these waves. Okay, to go back to our ABCs, right? Whereas over here, I can have bilateral symmetry, but I can't have C for an eigenstate. Now you can start putting, we'll do that later, but right the way it is, eigenstates are single and can't move. Okay? All right. So get this thing put together, wrapped around. We can see that this is a very interesting problem and has probably more physics in it than this one. This one's crippled. This is a crippled system. The eigenstates can't move their phase anywhere. Okay, no current in an eigenstate. These superconductors, if it's a charge. Okay? Sort of a very delicate superconductor. Okay, so this one forbids m equals 0. This one allows 1. And if we're going to do the p squared over 2m with p equal to h bar k, k being an m, we're going to get an m squared right there. Okay? And let's see if there's anything else I should be saying. It's probably okay. The L equal to 2 pi would let this become an h instead of an h bar. H times frequency, h bar times omega. And then the boundary conditions will give it. We'll finish that in a minute here. In fact, there it is. Fundamental Bohr angular frequency, 2 pi nu 1. And the interesting thing, and as I have to push this in a little bit to make it register, the idea is that we're going to take that 0 to be defined as 0, so you could just drop it out of this difference here, but always remember that any sort of behavior that we have of these things, differences like this, are the frequencies that we can see. We can't see just an eigenstate because we're not allowed to look at the phase. Okay, now I have on the screen there a moving picture that shows the phase, and this is a real failing of all of the quantum mechanics books, that they don't have a picture, even if it's just a snapshot, like the one shown right here. So this is not an infinite square well. Infinities are hard to make on a computer, but it's got some pretty high barrier here and a pretty small evanescence. You see, if I made that higher and higher and higher, I could pinch off this exponential evanescence here and make a wave that's like the one
on the infinite square well, but you have to go to infinity to make a perfect zero right at the boundary. Now you might have noticed that this isn't a very square well, at least it is the dots that represent what we need in order to do. This is a CN problem being solved here. It's being coarse-grained fairly coarsely, just so you can see how this program works. This program is a CN analog for continuum wave functions. And with n equal to 24, which is I think what I've got right now actually, it's still pretty good. And it will show the quantum mechanics that we need to learn for this particular lesson. But there sits the phase inside there. The real part is oscillating up, and then pi over 2 ahead is the imaginary part. You see the lighter colored curve is the imaginary part. There's a real part peeking out. Remember that our phasors are real this way, imaginary this way. We've turned them 90 degrees to show a transverse wave. So that's the ground state over there. The envelope of this wave, which will become the probability, is not changing. The phase is doing what phase does, oscillating at its eigenfrequency. So that's what's called a stationary state. And all of the states that you see in the quantum mechanics books that are being plotted as eigenfunctions are stationary states. There's going to be in this little well here at least 2 or 3 of them that can show. And I might as well show a couple of those just so you see it. I'm going to 0 here. Then I'm going to go up and set a phasor for number 2. And there's a wave that's going a little faster now, but it is a eigenstate stationary in time as far as its probability goes. It's the square of this thing would be more rounded than this, but that would be the thing that you would measure after many times you've killed it. And then the next one above that, I will 0 them so we don't get mixtures, is this one with 3 half waves. You see, that's what you get with this one right here. This is n equals 3. Looks pretty much like that, except for the evanescence, which has gotten bigger because we're approaching the top of this barrier when it can get out. This one can't get out. This is a prison. This is a high security prison. Abu Ghraib or something like that. Okay, sorry. Poor analogy. But the idea is this one can get out. Or at least it thinks it can. Okay? So, that's the situation we have. I will 0 go back to the ground state, which has some 0-point energy. That 0-point energy can be seen right here. It's just a little bit above 0. Okay? Not too different from about half, but it's less than half. It's not a harmonic oscillator. You can see that the spacing gets bigger. It's more or less quadratic, just like this one is quadratic. This is perfectly quadratic. That one is only approximately, because it's a finite well, finite top barrier well. Okay, now let's look at some of the dynamics. First of all, this is a picture of the maximum security prison with a 0-point energy, okay, which we work out just from our eigenvalues that we had before, okay, and then the next stop is this one, which is 4 of those units. So the difference, the beat energy, the energy you're going to get if you excite both of these at once, is 3 times the oscillation period of the phase at the 0 point. Okay, and then this one is 5 right here. 9 minus 4. These go as square. The frequencies go as square. Okay. K squared is n squared times the coefficient. Okay? So that's the sequence of eigenvalues. Now we're going to take differences of those. 2 squared minus 1 squared. It's 3. Okay? And this is our fundamental of 0-point frequency. Fundamental Bohr, if you want, 2 pi nu, and that's what we're talking about right here. Okay? So this is a picture of what's going to happen when I mix the two of them together. So let's take a look at that. What I'm going to do is just simply excite this one to the same amplitude. This is called maximum saturation. This is a saturated transition that we're doing here. We couldn't do this kind of stuff until lasers came. But there's what you're seeing. It's a slashing back and forth due to the fact that the frequency of this phasor for the antisymmetric state is faster than this frequency for that one. And so you get a charge distribution that's oscillating back and forth now. This is not a stationary state. This is a supreme example of a non-stationary state. Now, it will wiggle even if I just put a little bit in there. Right? A tiny amount, okay? Even smaller amount. You can't even see I have anything in there. And that's the way atomic physics used to be, that we could excite this thing to 0.01%. But it's enough when you have there's so much charge that that's enough to make light. That's enough to make radiation. Most of the things in this room are not excited to anywhere near a 1%, yet they're glowing like mad. So that's the key to transitions, you see. It's the difference in frequencies that gives you the dynamics. Okay? Now, I'm going to go ahead and show the one that's further down there, but rather than put a stress on the camera, we will simply redo this particular case here with 2 wells. Okay. Now, this one is a little bit extreme. I'm going to fix it so that the top of the peak is not quite so high. I'm going to bring this down to 25 or so here, and run it again. That way you can see there's a tiny, tiny splitting between this state right here, the second state. Let's zero it out and start the ground state. And this is quite interesting to see. You see an in-phase oscillation between the 2 wells. So these are 2 square wells, not infinite ones. If they were infinite, there would be no value inside there. The evanescent part of the wave is making something happen here inside the barrier, okay, on both sides of each barrier or each well, okay. And now what I'm going to do is add the second state, and I'm going to add it big time. I'm going to add it just the same as this. I'm going to take it up to about that amplitude right there. But what I'm going to do is I'm going to swing the phase around so that it's almost completely zero on the right-hand side. Okay? And that I do by getting these 2 phasors set to 90 degrees. Now, that 90 degrees is not as serious as the one that we talked about that makes resonance, but it's the same idea. Okay, so there is practically nothing on the right-hand side. But there's a beat that's going to happen.
The beat is between these two tiny, very close levels of the doublet of the ammonia molecule, for example. Nitrogen tunneling back and forth. Okay, and you can see what's happening. This side is pumping up that side, and this side is 90 degrees ahead of that side, all the way to the point where this side of the well will have nothing. And we're getting to that point close now. And when it does, it'll go out the bottom and come out 90 degrees behind that one. So that one will be ahead by a right angle, or 90 degrees, and it will be the leader, and it will be driving this one. Again, this is a lesson that's not shown in any of even the modern quantum mechanics books. They're all busy copying stuff that was known in the 1920s.
Sorry. Did we consider there are two particles in two wells, or just one particle that can...
If there's any word that you should strike from your vocabulary, it's particle. The world is wave-like. It's only every once in a while things go click or boom, and we're going to show some booms here, where you say, ah, I heard a click, that must be a particle. No way. It's all waves. So this is one particle. Or a coherent state of many, if it's photon band gap. Many photons. Yeah. I mean, that's the real lesson for quantum mechanics with relativity, because what we call relativity. This is the system. And that's the way it behaves. And it has a classical analog, our two pendulums, right? This is one pendulum, that's the other pendulum. It's just a lot more complicated because I really have an infinite number of these things, right? Or nearly an infinite number. Okay? Does this make sense? Yeah. All right. Well, you can see that once we get this understanding, we can begin to think about putting more stuff, exciting more of these. But whatever I do, you see, whenever I excite anything here, if I go zero this thing out, start the ground state, which is where it would like to go if it's given a chance to radiate away, and then start something up here, say. All I'm going to see is one frequency, the difference, the beat frequency. And that one looks like it has a dipole moment that's radiating. If instead of doing that one, and I did a pretty good job of killing it, I did this one, which has also even, I get a quadrupole radiation. That's a quadrupole oscillation. Two even states. Again, only the difference between them showing meanwhile, all sorts of hell's going on inside here because the phases are quite weird. But the outside is very classical, semi-classical. Okay, let's come back to the main one. I'll zero it out for the time being. And we'll go ahead here, point out what the numbers are, and then what I want to do is I want to add 100 energy states. We're going to go from 2 to 100. Okay. Well, that's going to take a little bit of algebra. I'm going to be coming very close to making an approximation to a delta function, Dirac's delta function. This XA here, if this is a continuum, and we're talking about the usual square well of infinite variety, which I've indicated here by broken concrete around the jail. I call this ultra-thin prisoner M. Okay, the mass, your particle, is a prisoner. Okay, and the prisoner has been made very thin by exciting 100, and that means 100 squared, 10 to the fourth energy. Okay? So we put a lot of energy into this thing to make him thin. Okay, but so essentially what I wanted to say is this is a bomb waiting to go off. I've just frozen the time for a moment here. And we'll see that the little distances here, 2 times those distances is 2 pi over 100. Okay, so here's the state, this explosive state, atom bomb, if you like. Okay, and there's its wave function. This is basically its wave function in Dirac notation. Okay, and the scalar product of those two is a delta function. That's the wave that we have right now. Very sharp wave, which we'll work out in detail. Okay, I'm going to use the completeness relation and stick 1 between x and a. The sum over n to infinity in this case would be the bras would make me have a completeness relation here. This is what you would call a completeness relation. Okay? Now, this thing right here, that is just the wave function sine k over a. Turns out I didn't discuss the normalization, but it has a 2 over w, where w is the width. Okay? This is w. I should have marked that. In any case, this is the amplitude of the wave functions. This is how much of each of these wave functions, sine kx, with the coefficient. So that coefficient right there is just the wave itself with its normalization written. Okay, so we have here a sum over n to 100. Wherever you get tired of adding wave functions, okay, we just did 2 over there, now we're doing 100, okay, n to 100 of these, the coefficient and the wave function, the coefficient being this. Okay, so that's what we've got. That's the wave function for the bomb, the atom bomb. Okay, now we're going to replace the sum here. What we do is we say n is equal to w pi over k. That's the boundary conditions. Okay, and I can replace a delta k, which is a 1 that's not explicit. Imagine I'm summing here delta k times this. Delta k is 1. Okay, that's the interval, quantum interval of the summation. And then I just rewrite that delta k as a dk and then pretend I'm playing calculus here. So I get an expression that involves an integral, which I can do, an elementary integral of sines that I can do to get a quick calculation. This is just one way to deduce what the actual function of the atom bomb is. And it's a good approximation, but it's not as good as some other ways that I'll be talking about later on that involve the group theory. We're just doing the ordinary quantum mechanics here. So I'm doing an integral of sine ka sine kx, which is cosine x minus a cosine of x plus a, trigonometric identity. We'd be normally using complex stuff here, but I'm just doing it the old-fashioned way. Okay? So when I finish doing this integral from 0 to k max, 0 to 100 basically, okay, I'm going to get this minus that. There's this k max x minus a, we've got k max x plus a, okay? And for x equal to a, that is in the neighborhood of this distance here that we've chosen, this just boils down to sine of x minus a over x minus a. Okay, I'll just leave out, this is the one that has the smallest denominator. This has a large denominator, so it is down here in the noise someplace, but this one's huge, okay? This is the peak region, around the peak at x equal a, okay? So, that's what we are seeing right here. Now, this is what I call the last in, first out effect. The last K max value that you added, which in this case is 100, dominates inside this pulse. All the other K gets smothered by interference with their neighbors. 99 gets killed by 198 on either side. Then 98 gets killed by 97 and 99 on this side. So you literally see here things that have a delta x 2 pi over 100. That's obvious from this function, but this is why. This is a quantum effect. If you suddenly cut off the distribution, then the only thing you see is what's on the skin. And this is analogous to the fact that you can treat band theory, where you have a whole bunch of electrons in a Fermi sea, and just worry about the electrons on the surface. They're the only ones that you're going to see the waves for. All the rest of them don't show any behavior at all. So, you know, a lot of lessons that you get to learn with this. So this is the function for x close to a, okay, in the neighborhood of a, okay, and the peaks goes to 0 on either side, a plus delta x and a minus delta x, the half-width delta x. That's what we're talking about here. This is 2 delta x, a full width. That's 2 pi over 100. Half of it is right there. There's the width that we're seeing just of this peak. Of course, there's also a width that you might assign to that, and that makes a little bit of this not quite exact, but it's hard to be exact about uncertainty. So, sine of k x max delta x equals 0, which implies delta x, quantity, times k max plus or minus pi, or delta x equal plus or minus pi over k max. There's another way to write it. And k max, we'll call that delta k, those two multiply up to pi. So there's the uncertainty relation you get from this approximation. Okay, if you want to use a delta p instead of a delta kappa or k, you got to put a pi on it, an h bar. That those two together make h over 2 for this uncertainty. That's the infinite well uncertainty. Okay, delta x over delta kappa, however, is 1/2 by this argument. Remember, we got 1 before because we were just counting this side. You need to count both sides. Okay, all right, so what's this thing going to do if you turn on time? It's going to explode. And you wouldn't ever expect anything to do that. It's going to do that too. But it's going to take some time for that. Here's what happens. Okay, now let's look at this graph here. The red line is the magnitude. That's the square root of the probability. The blue line is the real part. See the blue line inside there? And the cyan line is the imaginary part that's roughly pi over 2 out of phase with the real part. And you're seeing the kinks of 100 kinks. Okay? So this is 0.0004 of the fundamental frequency. The fundamental frequency being that oscillation we were looking at between 0 and 1. It's we're talking about 4/1000ths, 4/10,000ths actually, of the beat period, okay? Really defined. This is a bang. And this shock wave, if you will, has a very linear look to it, which we need to say some words about. Okay? So here's the fundamental frequency, okay, 2 pi over that omega 1, or 2 pi h bar over the energy number 1. That works out to h over h squared, 8 pi omega squared that comes up on the top. So this is the actual fundamental frequency that we're talking about in units that we're used to, more or less. Okay? And the classical velocity associated with any motion in this neighborhood is the group velocity, the derivative. Now this is an approximation. What you'd really be using is delta omega over delta k. But we're so close to the place where the deltas are, and they're small, 1/100ths, so we can get away with that. We can just take the derivative of our dispersion relation, which is quadratic, the derivative of k squared, okay, times h bar squared over 2m. We can take the derivative of that with respect to k and be reasonably confident we're getting close to an expression for the velocity. So when you do that, you get something that has either h bar and pi over mw, or else, since h bar is h over 2 pi, I get a simple expression involving h and n, and 2 times mw. Okay? So that's the velocity that we're talking about. We can plug numbers into that. Now what we're really interested in is the classical round trip time to go out to w and come back. Okay? That is going to be an interesting number. That number is very close to the fundamental period. In fact, it's fundamental period over 2 times n. N being 100 here, okay? So that fundamental period that goes with the fundamental frequency, omega 1, okay? That's what we're dealing with here. And if you work that out, for one-way time, it would be half of this period, okay? One-way time is 2 over 4n, okay? That's about 0025 tau 1 for n equal 100, okay? And we're getting close right here, okay? There's 0.0020, and we're not quite there according to this line. You see, at 2.5, that's pretty accurate for estimating a shock wave, a quantum shock. Okay? Again, why don't the quantum mechanics books do this? This is the real fun of quantum mechanics. It's when the thing is really alive. I've got 100 here. Okay?
Sorry.
So, again, last out, last in, first out. The last in was 100. 100 is the first out. Okay?
Are we looking at the time evolution of the wave back packet?
Yes. The same way we got the time evolution of 2. All those 100 phases are going faster and faster, and we're adding them up.
We don't know what kind of phases contains in this. It is a typical one.
There's no difference in the kind of phasors, except for frequency, as you go up the ladder. It's just that the frequency is going to go up as the square of the quantum number. Mm-hmm. Right? So if you think of this jail that this thing's in with these ladders, you see 1, and then 4, and then 9, then 16, right? And you go to 100, okay, 10 to the 2, you're talking 10,000. So if you've got 1 meter for your first step of your ladder, you've got 10,000 meters for the energy that you're putting in, thinking of it's a gravitational analogy, right? You're talking about higher than the highest mountain in the world, if this is 1 meter for the first step, right? So, yeah, the only thing that's enormous about this is the amount of energy we put here for this poor little prisoner M. It's nothing but Fourier adding up of the phasors, but those up there are really going, right? 10,000, right?
Might be smaller amplitude according to your distribution. But
And our distribution is putting equal amplitude in every one of them.
oh,
right? That's important to notice here. You're thinking Gaussian, which we're going to do next. Gaussian, much tamer, because then we don't have the wrinkles. We can smooth those out. That's what Gaussians are for. So, does this make sense so far? Although it's crazy, it's marvelous, right? But you ain't seen nothing yet. Here's what it does, okay? Now the 0 point T1 is just enough time for particle in these En level to make 2 n round trips, okay? The 0 point tau, this one right here, we can make 2n times that, and that would give you this time, okay? The periods for the ones that are way up there are much shorter, okay? So 2n times these fast guys, okay, gives me a full long period. How long it took for our system that we showed over there to do its trip over and back. It's 1 beat, okay? So in T1, the ground energy level particle does 2 round trips. The 2 does 4 round trips. The third level phasers do 6 round trips. Each one of these things giving more and more round trips until finally you're up there at the really high energies where it makes n round trips. So at time T1, M and N goes a full revival and unexplodes into its original spike at x equal 0.2 of the width. Okay, so just to say that, it returns to what we had initially. Unexplodes. Now we'll see simulations of this shortly, but that's clearly what has to happen. And you see, with this spectrum, since we have all of the frequencies given by a constant, the same constant times n squared, all of those phasers, when the bottom phaser goes 1 trip around, okay, the one at the top is gone 100 trips around. And they end up at the same place. Every one of them ends up at the place they started. That's called a Poincare recurrence in classical mechanics. If you've got a bunch of frequencies that are rationally related, there is a time when everything comes home. And then that same time again, they'll all come home again. So this is an amazing beat. And this thing has unexploded to that. But you still haven't seen everything. This Bohr thing will explain
How many frequency are there? How many frequency are there in this packet? Are they continuous?
100.
100?
Yes, that's what we did. We added up 100 levels.
In one hertz.
Yeah.
In 1
Starting
hertz.
with the number 1.
In 1 hertz we have.
It's as though I turned on, and I can
It's not in
actually
1 hertz. It
do
is in
that
1
right
over
here.
Tau 1.
Pardon?
It is in 1 over tau 1.
Yeah, tau 1
That
is
is
the period associated with nu 1. Okay? And nu 1 is just the first gap. 0 point energy in this case.
Mm-hmm.
Okay? At half of this, at 0.5, I get this. Before it does this, it does that. Now this really had me puzzled. After only 50 round trips, M's wave does a partial revival and makes an upside down delta.
And it is located at exactly the same distance from this wall as this one is from that wall. Now, we've got to understand this. I'm not expecting you to see this. It took me a while to see what was going on here. And the clue is we've got to do the Bohr rotor to understand this, because the Bohr rotor contains this problem. And it's easier. The Bohr rotor is much easier. It's got the symmetry.
Sorry, if it is a particle in the infinite well, shouldn't it
Yes,
be?
the
Yeah.
infinite well goes
Yeah.
way out
Shouldn't it be,
there.
no, shouldn't the E3 level particle 9 round trips? No, the
Well, we are at 30, we are at 10,000 meters, right?
no, I'm talking about the upper. I mean the top.
Oh,
Yes, this one.
This,
The E3 level particle, I think, should make 9 round trips. It is N2. I don't know.
oh, you're right, you're almost right for the energy,
Yeah.
but you're not right for the group velocity. The group velocity is the derivative of the frequency with respect to k.
Oh.
D omega dk. Actually delta omega delta k, but we're doing calculus a lot easier. Okay? So the derivative of a quadratic is linear. So the group velocities are all linear in the quantum number. Isn't that cool? Yeah.
Yeah.
And we'll show this another way with the Bohr. The Bohr is so much better at this. Okay. And then at a third and a fifth and a seventh, you get these crazy things. Now we really have to talk to Mr. Bohr. What is going on here? It's a kaleidoscope. Here at 1/9 of that period. They all pop up, 9 of them. Nine copies of whatever Fourier distribution that I started with, provided it's narrow. 9 copies, 7 copies, 5. What's going on here? Well, they're fractions. This is how you make this space-time fractal. So this is what we need to do. We need to look at Bohr rotor wave dynamics. But there's a little issue that I'd like to show first. And that is the geometry of that question that you asked. Why does my group velocities go up linearly? It's because the differences between the states, okay, for this dispersion, the Bohr-Schrödinger parabola, okay, peels away from the exciton cosine dispersion. This is frequency versus k. So we're looking at a very special dispersion relation, okay? The approximation to the hyperbola of the relativistic problem, which is the exact. Forget that for the moment. Everybody uses this for low energy stuff, so we're going to work with it. Okay? And what we're interested in is first the phase velocity, omega m over km. It's the frequency, there's the wave vector. Wave vector plotted this way, it's plus and minus m. Okay, for -1, -2, or start from -4, -3, -2, -1, 0, +1, +2, +3, and so on. Okay, so that's a map in the frequency wave vector space of all the quantum states. And the slope, omega m over km, that's mb squared over m, that's mb. It also is linear in m. Okay? So you get more and more slope, phase velocity, get more and more phase velocity as you go up. Okay? But what we're interested in, the thing we're going to see, this is just a statement of the momentum quantum, okay? What we're interested in with this dispersion relation, there's a fundamental showing there, we're interested in group velocity. And the big mistake that people make is to take Brillouin's formula, d omega dk, and apply it to a problem like this. And they couldn't figure out why nothing worked out. Just because it's wrong. When you're doing quantum mechanics, you have big delta m, sometimes 5, 10, 100, okay? Huge delta n's. Okay? Huge delta omegas, huge delta k's. That is what you're interested in. Half sum, half difference. Okay, in this paper we're talking about half differences of both of these, so the 2's cancel. I'm left here with m squared minus n squared divided by m plus or minus n. And that just comes out to be m plus or minus n. So there are the group velocities. There are the slopes of all of the connectors. All of the connectors between these dots are possible group velocities, ranging from 1, 2, 3, and 4 as I go between those two, ranging between 1, 2, 3, 4, 5, 6, 7 as I go between those two. So we get a number of levels, number of group velocities going up quadratically, but the slopes are going up linearly. And that's the correct formula, not that darn derivative. The derivative is approximation for low. Now remember, when we did light, everything was linear. Okay, so mostly you just went one way or you went the other, but you can mix those up too and use this this matrix here. I won't do that right now. I want to look at the one that's got this weird stuff going on. So we're doing a generalization now of the C2 beats, but there's a lot of them. That's what you see with this problem in space and time. You see something that's piled up here, and then it ends up piled up at pi. Then it comes home. So this is the mother of all symmetry, C2 here, showing its beats. That's all it has. It has 2 levels, so it only has 1 frequency. And makes a slope this way and that way of zeros. These are the zero regions. Now, we have more to say about this, because this is really weird. You've got a bunch of stuff here. It sort of gets all mixed up a little bit and appears over here. And then gets all mixed up around in here, and it appears back at the center. So that's a revival that's worth looking at in more detail, but we've got other fish to fry here. So this is a space-time view of what we just saw. Okay, with, in this case, only 15. I didn't take 100 here. Just 15, plus and minus 15. So I've got a sine x over x here with a 2 delta x equal to 0.04 times pi over 2. Okay, so it goes bang. There's a shock wave coming out there. You can see the shock wave lines going at 128th of the fundamental frequency, which is 1 here. And then at 1/64th of that period, you see that. And as you, I'm actually showing this thing at all the way up to t to 1/10. Okay? So this is what is called in the laser jargon a boxcar spectrum. There's your boxcar. Okay? You know, it's a railroad terminology, right? It's just a box, right? And I stopped this thing at actually 16. Just stopped it. There's no more after that. What we need is something to smooth this out. This is really quite complicated. Boxcar spectrum. Very complicated. I mean, there's some simple things that you see, but this is a mess. Let's compare that with this. This is what happens if I use a nice Gaussian wave. I get a Gaussian momentum distribution, and this is gentle. There's no m here like 100 that stands out. So you don't see the wrinkles. Instead you see little flying saucers. That we can understand. Gaussian wave has a Gaussian spectrum with comparatively simple space-time. Now we have to discuss the Gaussian properties. We're going to do that real fast.
What is these pictures? If I can understand the picture.
Well,
The dark ones, the
let's
bright ones.
wait just a
And
minute.
why they
Yeah.
change
Zero-
vertically?
zeros are indicated by white.
Zeros.
Yeah, or very near zero. When it's a low amplitude, it comes out white.
And they
And I
are-
recommend you do that. Remember how the zeros are the ones that give us our relativistic coordinates? The rectangle, the squares, the chessboard, and the, transformation and all that kind of stuff. Zeros are really powerful. That's the way it is in the wave world. Where the particle is usually useless. Okay? So you'll see a little bit of particle trails here, but they're broken up because of the oscillations and interferences. But the zeros, you can't kill a zero. A zero is, immortal.
Oh. They are different, I think. Vertically something changes. The number of frequencies.
These are fractions.
Oh, the fraction
15ths,
between
14ths, 13ths, 12ths. Okay,
But
we're
the
just
overall
getting
frequency.
started.
frequencies.
The orchestra is just warming up here.
The fraction between frequencies. or-
Yes, but we need not just
Huh.
1 over, we need 2 over, 3 over, 4 over, 5 over. We need all the fractions. They're all going to play out. The wave is going to find all of the rational numbers within about that much. All the rational numbers up to a little past 16. 16 is sort of our inflection point on the Gaussian. Okay, the width. And we got to talk about that a little bit. I'm going to go through this real fast because it's something you need to study on your own. But now we're going to suppose that we have a uncertainty spread here given by this coefficient. We're going to use a Gaussian m squared over some parameter, momentum parameter width. Okay? So we need to evaluate this the way we did the boxcar spectrum. Okay? So the idea is to complete the square in the exponent here. Okay? You put this im together. I want to complete the square of this quadratic. That's the trick. That's the algebraic trick. Add and subtract this quantity right here, and you've got a binomial here and this thing hanging off the side. Okay? That's the basic idea, is that this sum right here, okay, over m is being multiplied, the whole thing, by that. Okay? So we extract the binomial from that, and that's the thing we're going to play with. We're going to fiddle with that. The basic idea is that this thing right here is a distribution in angle, whereas this was a distribution in momentum. So this right here is what we want to look at. It approaches an integral like our other problem did. Okay, so I make a sum over m into an integral just like we did before. Okay, the momenta quanta of k are still the same. That hasn't changed. We're just dealing with this. So then I can let this be let this big K here, sort of complex K, give me a dk delta p dk. Then this thing integrates very nicely. Gaussian integrals, what we're dealing with here. Okay? This is the square root of e minus x squared, this is that. I can turn that into something I can integrate in elementary means. So that is what we get. This is the wave function that we get. We get it multiplied by that parameter, and then we get e to the minus Gaussian with that parameter there. But we got to turn it over. We got to turn it into a del that has to do with angle. Okay? So this is a definition. We're going to call it del phi 2 over del p. Then this can be turned into that. And you'll see that del phi del p equal 2. That's our uncertainty relation, Gaussian uncertainty relation in angle. Okay? And this will work very nicely for both of these, but the Bohr is what we're after. Okay? So that is
the deal here. All right, now we're going to do some animations of these things. This is just with 2 levels here. It's Gaussian, but you see I do very little of this. You can hardly see it. Okay, so this is when delta M is 1.5, less than 2. We've got a Gaussian there. I only have 2 frequencies. Just count one side. There's the other side there in order to make it balanced. So there's no chirality in the waves on the ring. Okay, putting that in makes some interesting stuff too. Now I've come up to 3. I've got 0 and then 1, 2, and maybe 3. I wouldn't count the 4 or 5. Okay, so 3. Now I can start to see fractions with denominators up to and close to 3. I see a 1/4 there pretty well. 5th, I can sometimes see it, but you'd have to know it's there to see it. 3, 4's pretty good. 3, 1, 2, 3. I'm seeing that. Okay? This is the fractal building. Okay? There's 9. Wow. This is what we need to look at. Okay? Now remember, this is wrapped around a ring. This is the Bohr problem. So we've got this wrapped around a ring. You see, it starts out with the thing at the bottom here. Okay, I've got the wave completely tied up in a little Gaussian that's right here. We're going to see that in the animation. It's going not bang, but sort of boom. Nice linear thing here. A little bit of wrinkling, and then it's going to build all of this stuff here. Because you see, it goes bang, comes around the other side, and interferes with itself, and does that over and over again. That's what's going to happen to make all this stuff. And we need to analyze that. It's really cool. So let's go ahead and do it on the thing. If you have these notes, you can just click on this, and it should bring it up. I'm going to click on this one, because that will bring up the Wave-It program with the fractal carpet. But here is a look at the Gaussian on a circle, you see. It's all piled up in the North Pole. Okay, starts with a Gaussian at phi equals 0 on the Bohr wave ring, and then expands with the beats. Okay, so let's go ahead and see if that'll work for us. There we go. And it's just starting, okay? Now it's come around to the South Pole and starting to interfere, so we're getting wrinkles. And now the wrinkles are leaving their own zeros, you see? And this is why you want to plot the thing so that the zeros are white. Don't try to plot them as dark, or it's really hard to read, unless you have color contrast between what color you're using for the wave. So there's up to 1/9, and you can pause this at any point. Let's try right there. Oh, I guess I can't do that. Oh, I forgot where the pause is. Thank you. I'll pause.
There's a 3. Hit it. Oh.
Pause at
I catch another one here.
Well, I missed it. I should have released. You have to click and release, right?
There's one.
There we go. Okay, 1/5. We're 1/5 of a way through an entire revival. And what do you see there? A pentagon. Right? You see 1, 2, 3, 4, 5 zeros. I don't count the ends because it's wrapped around. Right? You start count 1, but not the other. Right? Okay? Starting to make sense?
Yes.
It makes sense for just the 1 fractions, but what about 2, 3, and 4? We already have 2 11s here. If you look real carefully, you'll see 11 little tiny zeros in there. But our distribution is sort of beyond that. We don't have that many Fourier components right now. Okay, let's let her go. In a little while here, I'm going to keep my button on pause. There's 2 9s. That was kind of interesting. That's 1/4. right there. Okay. Now 1/4 should have 4 zeros, but it's even, so it doesn't. It gets rid of its 2 and has 2 big fat zeros. And that's what makes the flying saucers, is those nice Gaussian zeros. Okay, you see all those flying saucers everywhere? It looks like they're being invaded from space aliens. Okay? And this is going to keep up. The next stop will be 1/3. There's 11. You sort of can see the 11th there. It's broken past there a little bit, but that you can count that. That's 11. So that's a pretty clear. There's 2 7ths. You're going to see 7 with that. There's 3 10ths. You can see 5 with that because 10 is even. We're coming close to
No.
3. Okay? Now you see flying saucers that are roughly 2/3 of those flying saucers. Okay? It's odd, so you get 3. You get a triangle, right? You can see this is all going to meet a big zero fest right here. We started with the zeros here, we're going to end up with the zeros there and the peaks over there. This thing's going to invert. The whole wave is going to pile up and come up down here on the South Pole. Let's just let her run. Okay? That's marked as 4 11ths. That's marked as 3 8ths, which made a 4-fold thing. 5ths, there's a pentagon again. It's not quite the same position as the 1/5. There's 3 7ths. Wow, this is symmetry. There's an 11th again. There's a 13th. That's really hard to see. We don't have anywhere near that many going here on this one, I don't think. I forget what we had for this one. Anyway, we're getting close to the 1/2. Now this whole thing is going to happen again. The 1/2 you saw there stopped at the South Pole. Okay? So this is something to look at. And that's what we need to, we have about 5 minutes, I think, to go through quickly the analysis that you can use to figure this crazy thing out. Okay? So I'm going to return to the lecture just here and just point out where these things are in periods. This is 1/10 of T max. T max is the time for this thing to all pile back again on the upside, the North Pole. Okay, there's where we just were, and I stopped at 3/5. There's 1/5, 2/5, 3/5 of the whole period. The whole period would be up there close to the ceiling of the room. Okay, this is halfway. I've got to go that much more. Okay, and there are the fractions. They're all being displayed with this particular distribution that has a number. There you can see the inflection point is there. I only have really about 6, but twice 6 is 12, so I will be able to see something in the neighborhood of 12, with the 13 being about the limit on this little graph. Okay? Now here is a geometry of this, where I am tracking zeros with the dark blue and the black, okay? And I'm tracking particles from the starting point, which is right here, where the packet blew up, okay? Exploded the particles. Do you see any particles here? You have to stare real carefully, but they're there. First there's one going right up the center, that dark region. Then there's you don't see the dark region very well there, but you do see a dark region right about there. Okay? And then you see another one over here. Okay? So you see a half, you see a fourth, you see an eighth. You don't get to see the others. But the zeros show everything. Now we got to figure out what this is doing. how do those fractions all fit together? This is where we need to understand fractals. And this is, as I call it, so rationalizing the rationals. Okay? Basically, you pick any denominator that you can see, whatever you can get d as big as you have set your Gaussian, your denominator. You can set your denominator in anything. Then you'll have numerators that are multiples of that. This is a way of going this way. It goes this way, and then it returns and goes this way, and then periodic, you know, it's got to return. This is a topology of a ring that's been opened up. Okay? And then you can go the other way, too. You could have something making these lines here. The spacing is 1 over the d. Whatever that denominator is, that determines the spacing and the slope. N over d path, all of them, n over d2 path has slope 1 over d2. This has a slope of 1 over, as spacing of 1 over d. So that's just periodic motion is all it is. We have to figure out where they cross. That's what we've got to figure out. That's where the action is. That's where you're getting the revivals. Okay? So the n1 over d1 path slope is minus 1 over d in this case, and this one has a path slope of plus 1 over d, its denominator. So it's numerator over denominator. That's the fractions that we need to understand. Okay, so there's a typical line. N2 over D2 and N1 over D1. Here's the equation of it, the intercept form of the equation. The slope, 1 over D2, is equal to its value minus time. Okay, well, this time right here. Okay, and 1/2 minus the actual value of the angle where they intersect. So we've got a time thing we're going to solve for, and we've got an angle, the x-axis on this plot that we need to solve for. We've got two equations, it's easy to get that. Here's the equation that we're solving. Okay, take these two fractions, we'll kill this part right here, and get an n over a d1 over a d2 with a minus sign. I'm going to divide these two. Okay, got rid of the phi. Now I can solve. Okay, so I got to multiply that thing out. N2 over d2 minus t. Okay, equals this thing multiplying that thing. Okay, and I've got N2 over d2 minus t, and then I got N1 over d2 right there. So I can get rid of the d2. N1, N2, d. There's a numerator plus the time times the denominator sum. Okay, there's your answer. That's the time. This is called a Fourier sum. You're adding two fractions, Fourier-like. And your students will, you know, the American students will more than half the time add their fractions this way when they're actually trying to get numbers, right? You've seen this, right? Well, this time they're right. That's exactly right. And then there's something that's like a cross product that's due to Ford. This is 1815, this is 1931. Now, they didn't derive it this way. This is such a cool way to derive it. As far as I can tell, they weren't aware. So here is the idea of what the Fourier sum really is. It's related to a vector sum. And then there's some circles that come up. So what we're going to do, for example, is we're going to say, okay, here's the universe of fractions. I'm going to plot the numerator versus the denominator. Okay? So there I go. 1, 2, 3, 4, 5, 6, 7, 8, up to, well, depends on how much you want to divide up the units to. If you want to divide it up into 20s, that means you have got a Gaussian width of 20. This is good. This is going to get you everything. So a typical fraction might be 1 over 1. That makes a 45-degree line pointing at 1.0. Okay? Another fraction, V2, that's 2, that's 1/2. It's going to come up here with all of its ilk pointing at 0.5. Okay? So here are two vectors. There's another one right there that's this time a 0 over 1. Okay? It just points at 0. But let's take a Fourier sum of those two. Well, Fourier sum is a vector sum. Okay? If I take the sum of V0, that's this guy, and V1, I get this guy. Right? 0, 1, and 1, 1, Fourier sum. That's a vector sum, 1/2. Okay? So the Fourier sum is not so exotic. It's just a vector sum in the universe of fractions. And this vector points to 1/2. Okay, now we can keep doing this. But there's something else funny happening here. Once you get a point here, here's your unit circles, tangent, okay? You go ahead and you run a line through where that intersects the circle. Okay? Circle radius intersects the V2 line. Okay? And where that happens, you draw a center of a Ford circle for 1/2. If you saw the movie Titanic, you have to imagine a picture of some very beautiful circles with a jewel between them. I put that anthropomorphic analogy in here so that you'll never forget this. Okay? But there's more jewels waiting on the other side. The next sum that we're going to do after 1/2 is 1/3. Fourier sum of those two. Okay, so I do that, intersects the unit circle, I find a point and draw another circle that's tangent to all three and the top. This is cool. This is cool. And there's a whole bunch more. You just keep doing Fourier sums, you create a fractal structure that identifies all of the key fractions up to a given diameter. That's neat. That is really neat. There I am up to 11. Okay? Getting tiny circles. You'll fill this whole thing up solid with circles, but in a very fractal way. All of the circles have a diameter of 1 over the diameter squared. And inside each is a Thales rectangle with exactly the fraction. This I discovered myself. I didn't see this anywhere. And we're making use of that for various things. So this is a quantized Thales rectangles, and there's a whole Fourier tree worked out up to 8, and you can, see basically you keep writing the fractions over and over again after you've made one, and then you just keep doing the Fourier sum to get more fractions. So this is something you should look at in 3D. You just let your eyes cross so that these two come together. Or these two come together, any one of them, you get a really beautiful 3D that goes to infinity. That's something 3D things usually don't do. Okay, the rest of this is just character theory for C3, 4. There's 3 showing the phase. These things show the phase at every one of those points. Every point on there is unique in this section and in this section. You can tell where you are by the phase. That's something you couldn't do with a Lorentz graph. Here's the same. This is C6 now being shown. And the subgroup C3 of C6 makes itself fairly obvious. You see these, this structure in there, repeated. You see, it's really quite amazing. And you'll see in this one, the even ones, C6. You'll see our old friend, C2, moving over, and in the process making these two. Remember the ones that were 45 degrees and then piled up there? So it has to be in there. C2 has to be in C6. It's a subgroup, so it has to show up. C5 has no subgroup, so when it goes, it just makes a whole bunch of things that are the same. Do something like C15, and it will factor. It'll show you it has a factor of 3 and 5. Wherever there's nothing, that's a... this is factoring integers by waves. This is when you make the Gaussian move off center. That's really weird. We can talk about that later. This is what happens if you have a bouncing mass, a huge mass and a very small mass against an infinite wall. This is just classical mechanics. But the velocity turns out to be inversely proportional to the space left. So this is analogous to the uncertainty condition. It is a classical example of the uncertainty a relation, and it is the uncertainty relation ultimately. And we might as well go ahead and show that. This will sort of be the end of the talk right here if it works. There's the big mass coming in and hitting the little mass, okay? And this is a velocity plot. Vx2, Vx2, x2, okay? Boom. 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 Boom, 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 boom. You make a hyperbola. That's the hyperbola product equal a constant. Now this is a little imperfect because it comes back with not the same energy. It gets lost in the integration routine. I was a little too fast there. So you see a concentric hyperbolas made by this. And that's what's going to happen as this thing goes back and forth between the two walls. We have actually this one bouncing off of the wall to hit this thing again. And the whole process repeats. Now with a slightly different arrangement of velocities. It's a cool thing to play with. Okay, I think that's about where we should stop at this point. I'm going to go ahead and return to the lecture to make sure there isn't anything here that you ought to look at. There's the actual plot of the double monster mash. It's the same as the single flipped over. And there's a geometry of it. It's really cool. And there's a lot of symmetry associated with this particular classical mechanical problem. This is the way I start classical mechanics. Learn about quadratic forms early on. Now, this is something we're going to have to put off. The character formula for UN is really beautiful. You're doing a sum here with U2, U3, or U5. They all are geometric sums that make a expression. This is an exact expression for the things that we were deriving before, the diffraction function, the sine x over x function. But that is a character. That is a very important character for our group theory. That's a character of the unitary group of arbitrarily high dimension. It's the king of characters, some people would say, for quantum mechanics.